StatMan here to go over the chi-square goodness of fit materials. All right, so it's probably going to be this blue packet right here. Probably going to be this, okay? What I did for the 26 year is I separated the goodness of fit test from the chi-square for tables. So if you're looking at Desmos, let me get it on here. If you type in inference, you have a goodness of fit test right here, and then you have a test for independence. This goodness of fit test is what I'm going to be covering right now with this packet. You're going to get a separate packet for the test for independence. Okay, you're going to get a separate one. And the reason is in the year 27, they have cut out goodness of fit from a standard for AP. So you won't have to know that. So this will go over all 3 days. I budgeted 3 days for this, but really it probably just takes 2. And I'm going to do it all here so you have the whole goodness of fit packet all together. So we're going to do that. All right. So here are the notes. Okay, oops, that's the bell. So now we're going to be studying the chi-square distribution. That's for categorical data. Now, a few things about this as you're taking notes. Again, stop this video anytime, of course. As you're taking the notes here, make note that that the distribution is skewed to the right. And at low degrees of freedom, like 1, it's heavily skewed. And that at higher degrees of freedom, it starts moving a little bit less, but it is a skewed to the right distribution. It is not a normal curve, okay? This is our 5th test that we've run. So let's go over the first 4. The first 4 was 1. The first test that we had was a t-test. And that t-test was a test for means. Remember that? T-test, kind of hard to write with my mouse. The second test we had was a 1 prop z. 1 prop z, okay? The third test that we had was a 2 sample t, I'll put sample t, and that's for a mean. And the fourth test we had was a 2 proportion, 2 prop z. Okay, those are the 4 tests that we've done so far, okay? Now, clear those drawings. Okay, now if those tests are easily seen here, okay? The test for proportions, I'm going to click on that. You can have 1 sample or 2. And if I go back and type in inference again, there it is. You can also have a t-test, and that's 1 sample or 2. So they're all right there. And what's great is that now we're on to the goodness of fit test. The next packet you'll get is the one for independence. That's for tables of dimension 2 by 2 or higher. We're doing the goodness of fit. Okay, so as you're writing this down, we have something called observed counts, O, and then we have expected counts, that's E. Now, when we get into the requirements, remember the SPIN acronym? So let me write that out again when we get into SPIN. The S is still representative sample. The P in SPIN is, of course, the population's got to be 10 times bigger than the total in the table. The I in SPIN is, of course, independent. That's the same old thing, independent, okay? And then the N in SPIN is not for normal. It's different. You want the number in the expected category to be all bigger than 5. You want them to be all bigger than 5. If they're not all bigger than 5, we'll take 80% or more of the expected bigger than 5. And we're going to go through that real easily. This is very easy to do. There's details that might bother you a little bit, but it's pretty easy to do. All right. So I have 6 problems here. I'm not going to do 6 of them. I'm going to do 2 of them, and then you should work on the other ones with just simply freeze the frame here and work on the other ones yourself, okay? We're going to talk about just expected cells right now, and then I'm going to get into HOHA later, but expected cells right now, okay? So here we go. A city council in 2A claims that they have an equal number of Black, Hispanic, Asian, Caucasian, other residents in the city, the same amount. So this is like an equal distribution. So if you take a total of these 26, 31, 27, 29, and 22, that adds to, of course, as you can see, that adds to 135. If it's an equal distribution, like I said, equal, you take 135 and divide by the number of categories. 1, 2, 3, 4, 5. And 135 divided by 5 is 27. So it's real easy to get the expected count. So in this test, you need observed data, that's the prompt, and you need expected data. And this is one style where you divide the total by the number of categories. The prompt will tell you how to do it. Okay. Now, if you go to Desmos, I got to remember these numbers here. If you go to Desmos and I do a goodness of fit test, now it'll make the column this way. I need these numbers: 26, 31, 27, 29, 22. 26, 31, I think I already forgot. 26, 31, 27, 29, 22. Now, you don't have to put I could put the expected in here, 27. If I click create test and I put the expected data, if you don't do anything, it'll do the expected counts automatically by dividing it all by the number. So the expected is right there. Okay. Now, the observed and expected data will eventually help develop the chi-square sum, which is our statistic. So we always have a test statistic of some type, and we're going to talk about that, but not right now. We're just trying to develop the expected data. That's all we're trying to do right now. Okay, so there we go. Okay, now, if I go back to this, the other style of prompt, it's actually the same thing, is this type, where you have percentages where things are supposed to happen. Okay, Mr. Stunder claims that 20% of his students earn an A, 60% a B, 15% a C, and the rest a D. Okay, so what you got here is the total is 35. Okay, so I need to multiply. So let me get these numbers in the in Desmos. Okay, so let me do this again. Type in inference, and I'm going to do the goodness of fit. I'm going to put the numbers in. 8, 18, 7, and 2. Okay, 8, 18, 7, and 2. Okay, now I need to actually do the expected numbers here because they're not proportional, they're not the same. I'm expecting, if you look back, I'm expecting 60 or 20% A's. So I got to go 35 times is the star above the 8, 0.2. Oops, didn't work. 35. Well, I'll have to do it by hand. 35 times 0.2. 35 times 0.2, I believe, is 7. Okay, so that's 7. Then I got to go 35 times 0.6 to get my B's. 35 times 0.6 is 21. Sorry, I'm going back and forth. It's a little aggravating, I know. And then the C's, I believe, was what, 15%? So 35 times 0.15 is 5.25. And yes, you can have a decimal in the expected, no problem. And then the rest are D's. What is the rest? So 20 and 60 is 80, 95, that's 5%, 0.05. So 35 times 0.05 is apparently 1.75. Okay, so this is a little different, okay? So if I go create test, we've got observed that the expect is already, I have them all there. I had to do that myself because they weren't the same, they were different. Those are the two different styles that you'll see in the chi-squared goodness of fit. Goodness of fit meaning how good does your data fit a preconceived notion, okay? So now with that out of the way, you can do C, D, E, and F yourself. Now, okay, C looks like it's going to be an equal distribution. So you're going to divide the total by 7 categories, okay? D is not, and it's proportional. You got to multiply the total by these percentages to get those numbers, okay? And then E is also proportional. You got to multiply the total by this, okay? And then F looks like it's an equal distribution, but there's no other information to go off of, so it's equal, okay? So step 1 in the math is to get the expected counts, okay? So take the time, pause the video, and work on all these and make sure you understand it with the answer key, okay? Next, okay, we're going to calculate the test statistic and the corresponding p-value. Now, Desmos is going to do most of this, but we're going to calculate the statistic together, okay? The chi-square statistic is a value. It's a whole number. And the larger the statistic is, the lower the p-value. So the bigger the stat gets, the lower the p-value. And we're going to talk about degrees of freedom as well. Here is the statistic for this, okay? And we're going to do this for one of these, just one of them, okay? So here it's O, meaning observed, minus E squared divided by E. And you're going to add them all up. O minus E squared divided by E. O minus E squared divided by E. I'm getting my calculator out here. Okay, so it's pretty simple. Now, like I said, Desmos will do it all for you, but you should know how to do it by hand. So I'm going to go to one of the easier problems that's smaller. I'm going to go to this problem right here with these 4 problems right here, okay? So, right here. Okay, O minus E squared divided by E. So that's going to be, for the first one, it's going to be 8 minus 7 squared divided by 7. O minus E squared divided by E, okay? So 8 minus 7 squared divided by 7. So if I do that, that is basically 1/7, 1 divided by 7, okay? Comes out like 0.14, 0.14, something like that, okay? And we're going to see that down here. So that's the first number, okay, for that one. Okay, let me clear that. Now, if you notice, if you go down here to the answer key, whoops, down here to the answer key, these are the chi-square terms right here for that, right there. I'm going to do all those for you. These 4 are the ones we're doing, okay? And then I'm going to add them all up, and you're going to get about 1.1905, okay? All right, so let's try that. So let's go back up here. I'll do the second one. Okay, I'm doing the second one. Okay, so I'm going to go 18 minus 21. So I'll write it up here. 18 minus 21. O minus E squared divided by E, 21. 18 minus 21 divided by 21, okay? All right, there's the second number. The third number will be 7 minus 5.25, 7 minus 5.25 squared divided by 5.25. That's the third number. And then the fourth number will be this one right here. And I'll write it over here. 2 minus 1.75 squared divided by 1.75. Those 4 terms are called the chi-square terms, okay, are part of the chi-square sum. So let's go down to the answer key down here. Okay, so number 2B corresponds with 3 right here. So these are those 4 numbers that you worked on right here. And if you add these 4 numbers, you will get a chi-square sum of 1.1905. Now, this one right here is the largest contributor to the chi-square sum. Okay, it's about half of the chi-square sum. 0.58 is about half of 1.19. Okay, the smallest contributor is this one. Okay, this is the largest contributor. This is the smallest contributor. This stuff does come up. And it's pretty clear how this works. If you go back up to the question right here, okay, the largest contributor was the gap between 7 and 5.25 is the largest. The smallest gap is here. That's all it is, where there's the biggest discrepancy. Okay, now you're going to take that chi-square sum, and I'm going to scroll down again. Okay, going to take that chi-square sum, and that's going to translate to a p-value. This is a test statistic. Okay, other test statistics are the z-score or the t-score. Remember how those are translated into a p-value? This is our statistic, 1.1905. Now, to show you how easy this is to do by hand, okay, we're going to do all this. You ready? We're going to go to Desmos. Okay, and this will be done automatically for you. Okay, so this was that problem. And we're going to run, by the way, contributions. Okay. These, when you click contributions, these are those chi-square terms that I did by hand. They're right there if you click contributions. Isn't that cool? When you run the test, it's right there for you. Okay, that's in the observed and expected area. And then, so that's great. So those are the chi-square terms. The significance test is this. The degrees of freedom, DF, is 3. Why is it 3? Because you take the number of categories and you subtract 1 to get 3. There's the chi-square sum. That is our test statistic. And this is the p-value, 0.755. That would be a fail to reject. And we'll talk about HOHA and all that kind of stuff in a minute. But that's how you run the test for the chi-square goodness of fit, called GOF. How well does my data fit a preconceived notion? Okay, so let me clear this, and we're going to move on. Okay, this is pretty cool so far. Okay, so now I've pretty much gone through kind of, the notes, the first part of the notes here. Now we're going to talk about the requirements and how to write HOHA. Okay, so let's talk about that, all right? So there's several ways to write it. One way is that you can write HO, the variable, is equally distributed, and HA, the variable, is not equally distributed, okay? Not, that means different. Not equally distributed means different, okay? You could write the variable is proportionally distributed or not proportionally distributed, okay? You can also write it this way. There's a lot of ways to write these. HO, there is no preference, and HA, there is a difference, or there is a preference, which we'll get to. You can write HO, the variable, the distribution of the variable is as stated, and then this is actually not consistent with it, not as stated. The variable is consistent as stated, or is not consistent. There's a lot of ways to write these, and we'll do samples of these, okay? Your conditions is still spin. Here is the only difference. We want all of the expecteds to be bigger than 5, all of them. However, if 80% or more are, we're good to go. Everything else is the same. And we're going to run through this in a second. Okay, now let's try to do this, okay? So we got observed and expected data here. I'm gonna make this real simple. So I rolled the dice 120 times, and I'm gonna make up the numbers, okay? 120 times. So we know the average would be 20 per. okay, it would be 20 each. 20, 20, 20, 20, 20, and 20. So let's say when I rolled, I got 15 here and I got 25 here. I'm going to make this real simple. Let's say I got 17 here and I got 23 here. And then I got, I don't know, 19 here and 21 here. Okay. So that's this adds to 120. And of course, the expected does. Now, the O minus E squared, the right here divided by E, I could do this all by hand. There's no question I could. Let's go through the process. HO could be, it could be the roll is equally distributed or not. You could say this. You can be creative. HO, the die is fair. F-A-I-R, fair. Sorry, it's hard to write with a mouse. And then H-A, the die is not fair. That would be another way to write it. Okay. Not fair means it's different. And by the way, this thing is always shaded on the right-hand side. Even if you use the word different, it's always shaded on the right-hand side. Not fair. We're trying to prove the die is not fair. Does this right here, does this roll count, roll distribution show that the die is not fair? I doubt it. Okay, so let me scroll down here. Okay. Here are your conditions. Okay, I've circled them by accident here. We have a representative sample of dice. The population is more than 1,200. I think 1,200 is 120 times 10, all right? Each roll is independent, and all the expecteds are bigger than 5 because all of these were 20. They're all bigger than 5. So we have met all the requirements, okay? You don't really have to fill this chart out. Now, we've done HOHA. We've done our conditions. Okay, so let me get let's see here. If I can get a different color here. No, they're fine. All right, so we got the HOHA. We got the conditions. Now we're going to run the test. To run the test, we're going to go to Desmos. Okay, so let me clear all of these numbers. Okay, clear all drawing. Go to Desmos. I'm going to type in the word inference. I'm going to go to goodness of fit. And I got to get the, I forgot the numbers. I think it was 25, 15, 23, 17, 19, and 21. I'm confident. Okay. Now, I don't have to write these in this time because they're all going to be the same number. So I'm going to hit create test. So I'm going to go observed and expected. There we go. By the way, when you write out the assumptions, you do have to write out all the expected numbers because you're going to say they're all bigger than 5, so you got to write them, okay? So there are the chi-square numbers, okay? The biggest contributor to the chi-square is the ones and the twos. They have the biggest number. The smallest contributor was the 5s and the 6s. Okay. Now we're going to run the test. Okay. So the test comes out right here. Okay. The chi-square sum was 3.5. The degrees of freedom is 5. Categories -1. So this is how you're going to draw it out. You're going to draw this skew to the right, and you're going to draw the test statistic, which is you're going to write chi-square equals 3.5. And then you're going to write the p-value right below. It's always on the right-hand side, 0.623. 0.623 is definitely circle it, a fail to reject. We do not have enough evidence. This is all the shading. We do not have enough evidence to suggest that the die is not fair. Okay, this set of rolls doesn't prove an unfair die. Okay, that's how you would draw it. Is that simple or what? Okay, so pause that if you need to, of course. Okay, so let me go back to this. Okay, so we've pretty much have I did all this for you, failed to reject, etc. And we answer these questions. They're furthest from expectations, the closest, all that kind of stuff. We've done all that. Okay. All right. Now we are going to go to let's see here, the next page of the notes. Make sure I got this right. So give me a second here. Let's go to the next page of the notes. Okay, so let me get this here. So the next page of the notes. I'll make this a little bigger. It's gonna be a little tricky to do here as I go back and forth from Desmos, but I'll get it. Okay, so the next page, 1, 2, yeah. This could be a question you get on the test. Okay. If you ever notice people are absent more on Monday and Friday, this data shows that. Okay. So this data definitely shows that people are absent more on Monday and Friday. All right, let's check it out. At the O5 level, is there uniformity or not? So, no problem. Let's go. Let's start with HO. HO, I would say, remember, HO is something that means the same. Okay. I'm going to put absences, AB, absences are the same each day. And then HA are absences are, I'm going to put the key word. Absences are not uniform throughout the week. Are not uniform throughout the week. They're different. That means different. We're trying to prove they're different. Does this data show a difference? So you're going to write this out a lot better than I did. Okay. Now, you clear that. The conditions for this. Okay. So I'm not going to write these out. You're going to write, we have a representative sample of days. P. I believe this is, how many days is it? This is 100 days. This ends up being 100. So there's at least 1,000 days to pool from, 10 times the sample size. I, all of the data is independent. And then N and spin, if you add 100 and divide by 5, these would be 20 each. So you're going to write out 20, 20, 20, 20, and 20. Okay? So they would be 100 divided by 5 is 20. All the expecteds are bigger than 5. That's step one. HOHA, write out the assumptions. Next, you're going to run the test. So let me get over to 24, 17, 15, 19, and 25. Okay. So I'm going to go to Desmos. I'm going to type the word inference in. Infer. Goodness of fit. What were those numbers again? Help me. 24, 17, 15, 19, and 25. 24, 17, 15, 19, and 25. Those don't look uniform to me, but let's check it out. Now, again, it's going to be the same number, so I'm going to go expect it. Yeah, they're all 20. If it's uniform, you would expect 20. Contributions. Looks like Wednesday and Friday are the biggest contributors to the chi-square sum. The smallest contributor is Thursday. People don't take Thursday off, anything unusual. Now, if you run the test, the p-value is large. There's not evidence. So you're gonna write this out right here, copy this out. You're gonna put the chi-square sum, put the p-value below it, and circle it 0.434, and then shade in 43%. And this is fail to reject HO at alpha 05. At alpha 0.05. We have insignificant evidence to suggest that employees are missing certain days more than others, that it's not uniform. Okay, repeat HA. That's all you have to do. Pretty cool, huh? So you are good to go on that. So there is that prompt, okay? So let's do two more. See if you got this, okay? So let's do two more here. Okay. That's that one. Let's do these two right here. Okay. So this one is another uniform one. A toothpaste manufacturer, they want to know if there's a preference. No problem. Okay. So HO is going to be that there is no preference. No preference. No preference means they're all chosen equally. HA is going to be there is a preference. Is a preference. Okay? And that would also mean that they're not chosen equally. So you can write it multiple ways. Your assumptions. S, representative sample. P, how many? 200? There's at least 2,000 customers or consumers. I, all independent. And N, I believe 200 divided by 1, 2, 3, 4, 5 is 40 each. So you're going to put the expecteds are all 40 in this case. Okay, all 40, 40, 40, 40, 40, 40. Okay, they're all 40. Okay, so all the expecteds are bigger than 5. We're good. Now let's run the math. Okay, so I got to remember all these numbers. I should write it down this time. This is ridiculous. My little brain. So we got 32, 30, 28, 58, 52. Okay, so let me write this down here. All right. Okay, type in inference again. Goodness of fit. Okay, here are the observed data. 32, 30, 28, 58, 52. Expected, I'm going to create the test. The expected, they're all 40 because we're wondering if they're all the same. Here are the contributions. Looks like this one, this category is the biggest contributor to the chi-square sum because it's the biggest number. If you run the test, there we go. This one, you end up with significant data. It's very small. It's under 1%. Okay? So this is, if you would write this down, this is reject HO at whatever alpha level it was. We have significant evidence to suggest that the toothpastes are not preferred equally. They are not. Okay? Very simple. Okay. One more prompt. Okay, so let me go back to this. One more prompt. Okay. M&Ms. As you may or may not know, M&Ms are not distributed equally in a bag, okay? These are the latest distributions, and I'm going to have to make up some numbers here. I'll have to make them up. So we got 1, 2, 3, 4, 5, 6 categories, okay? 6 categories. I got to make 50 out of these. So let's say red was 10, okay? So if let's say, whoops, sorry about that. There we go. Let's say red was 10, 10. And let's say brown was 12. Okay, 12. And there's a total of 50. Let's say yellow was 8. So now I'm up to, was that 30? 10. That's 30. Let's say green was 4. Green was 4. And let's say orange was 6. Okay. Orange was 6. So what am I up to? 10, 30, 40, and then blue was 10. There we go. Blue was 10. Okay. Now I got to get the expected values. Okay. So I'm going to multiply 50 times 13%. So, all right. So 50 times 0.13 equals 6.5. So this is 6.5 here for the expected, 6.5. Okay, so 6.5 there. And then brown will also be 6.5. Yellow's 14%. So 50 times 0.14 is 7, exactly 7 of those. 7. And then let's see here. Did I get that right? Oh, yeah. No, green is 16%. So 50 times 0.16 is 8. So this one is 8 right here. And then the orange would be 50 times 0.2. That's 10. Okay, so that's 10. And then the blue one is 24%. So 50 times 0.24 is 12. Okay, so I got to type those numbers into Desmos. Okay, so I'm writing these down on a piece of paper. So I got this 7, 8, 10, 12. Okay, all the expecteds are bigger than 5. So HO, you could say the distribution, DIS, distribution is as advertised. Okay. And then HA could be the distribution is not as advertised, not as advertised, meaning it's different. HA is always something that means different, not as advertised. Okay. The assumptions, same old thing, representative sample, population bigger than 500, 10 times 50, all independent, and the N, all the expecteds are indeed bigger than 5. We're good to go. Okay? So let me clear all this, and let me go to Desmos. Okay? So let me go to Desmos here. Now on Desmos, inference. All right, goodness of fit. Here we go. Observed data. 10, 12, 8, 4, 6, 10. Expected data. I have to type it in this time because it's not evenly distributed. 8, enter. 10, enter. 12, enter. All right. Create test. Okay. We got it all there. Contributions. Okay. The biggest contributor is this second category right here. That was a very large contributor to the chi-square sum. The smallest contributor is this one right here, the blue one. Remember, that's blue. That okay. No problem. Let's run the test. By the way, there is no confidence interval for this. So the p-value is 0.06. It's significant at the 0.1 level, not at 0.05. So this is probably, if it's 0.05 or 0.01, failed to reject HO. This data does not prove that the distribution is not as advertised. Okay? There we go. That is the entire note packet. This blue one, if you're looking at me in the corner there, is the entire note packet for chi-square goodness of fit, which is not a part of the 27 test, but is a part of the 26 test. Go get them, StatNation. Great job.